Hello, thanks for joining us at this webinar, Natural Gas Storage Valuation with MATLAB. My name is Amaya Davis and I'm a Senior Application Engineer at MathWorks. The goal of this webinar is to show you how MATLAB can help you deliver insight and analytics to your organization, and we're going to do it in the context of a natural gas storage valuation example. So as an introduction to natural gas storage, for those of you that may not be familiar with this area, the gas markets are highly seasonal. So if you look at a forward curve, for example, of natural gas prices, you'll see that the winter months tend to be at a premium over the summer months. This is the shape of the Henry Hub forward curve in the United States, and you can clearly see that seasonal pattern. And it really stems from the demand for natural gas for heating in the United States. So storage is an important part of this industry because it enables operators of storage facilities to inject gas during the summer months and the off-peak season, build up an inventory, and use that to satisfy demand in the winter. And because of the shape of this curve, there is a significant monetary value that can be attached to storage. This other graphic here, courtesy of the EIA, shows the locations of some of the gas storage facilities in different parts of the United States. Also highlighted are different types of gas storage facilities. The reason this is a complex problem is because there's a lot of different operational constraints in how one can inject and extract gas from these storage facilities. And that's coupled with the dynamics of the market make it a challenging problem to value contracts around gas storage. And so the focus of this webinar will be to look at how MATLAB can help us build applications that enable valuation of gas storage contracts. So let's set up the problem here. The goal of this case study is to deliver a front office tool to value and analyze gas storage contracts. I'm wearing my quant or analyst hat here, and I've been tasked to build this tool for others to use in my organization. If I go around and look at different alternatives for how we can do this, I notice that I can come up with a few challenges when it comes to building or delivering these kind of analytics. One is the accuracy of the models. There's a lot of different choices for models out there, things that can be easily implemented in Excel might not be the most accurate. And so we want to be able to analyze and verify the validity of these models. And at the same time, we want to be able to express our own views so that if you have any custom views on the market or views of choices of models, we need to be able to express that, and the tools we use need to be able to allow that. We also be able to extract insight from the analysis process. So it's no longer okay to just provide a number at the end of the day, but everyone wants to know how those numbers are calculated, what are the assumptions of the model, so those assumptions valid, how can we test them. We want to be able to scale computation because a lot of the times accurate models may involve more complex math, more complex computation. We need to be able to deliver a solution that can handle that. And finally, it needs to provide a simple interface so that anybody who can use it, especially in the front office, maybe a trader or somebody who's not as technically savvy with programming, should be able to use it. Oh, and one more. All of this has to be delivered in a short amount of development time. So these challenges are very real and can really impact how quickly these analytics can be used and leveraged for business decisions. So we're going to look at how MATLAB can enable you to build these analytics and address some of these challenges. So let's jump in and take a look at a finished application that meets these needs. And here's the application. As you can see, it's an Excel front end with a lot of MATLAB analytics built in behind it. The great thing about this spreadsheet is that I can give this to somebody who doesn't have MATLAB. They can still run it, do all the calculations, get all of the insight, do their work. So on page 1 here, we've set up the problem. So you can see we have a contract that goes from June of this year to June of next year. Our facility has certain limits, things like the minimum amount of gas or maximum amount of working gas that we can store, costs to inject and withdraw, and a capacity limit for how much we can inject and withdraw per day, depending on how much volume there is. So you can see if the facility is full, we can't really inject anymore. Likewise, if the facility is full, we can withdraw to the max, but if it's close to empty, that gets reduced. So some of the data that we're going to need to work with is we have information on the forward curve that we can use to take those positions. We're also going to import data for historical prices as well as options. So when I hit calibrate model, this is going to spin up some MATLAB runtimes behind the scenes that are going to import that data and calibrate our model. That includes estimating volatilities, correlations in a monthly fashion, principal components, and so on. So we have things like historical volatilities, implied volatilities, the correlation matrix between all of those different contracts. If you look at the volatility term structure here, you can kind of see that effect. The historical volatilities just typically decay, but the implied volatilities contain some of that seasonality in the volatility. This heat map on the right shows some of the structure in those correlations by different front months. So you can actually see that the way the curve behaves in July, or when the front month is July, is very different from the way it behaves when the front month is January. And it may no longer be sufficient to work with just aggregated correlation matrices. So this speaks a little bit about the need to be able to express your own insight. I want to be able to use models that that allow me to express my views. And finally, this is just the historic evolution of that forward curve that we imported. So we've got our data, we've calibrated our models, and we could do the valuation. There's three methods of valuation, which I'll talk about a little bit later in more detail. But for example, with a simple intrinsic optimization, I can have MATLAB figure out the optimal injection and withdrawal schedule that'll maximize my revenue while still meeting my constraints. So you can see these are injections and withdrawals, and they're below our limits. And so today I can lock in a value of 96,000 for the storage facility. This doesn't capture all of this, the volatility and the additional value from the motion of the curve. So there's a couple of other methods that could take advantage of that. So with the spread option method, we can use a model to price a number of spread options between every pair of contracts. So injecting in June, extracting in August, so on. And what this is going to do is figure out the optimal positions in those contracts, those option contracts, such that our net injections and withdrawals are within the constraint, but that we can extract a lot more value. This comes from the fact that options can never have a negative price, and so our intrinsic value is increased, as well as because of the volatility, we're able to extract a lot more value. We'll talk a little bit later about how we can monetize this and how it compares to the other valuation methods. But as you can see here, we have a little bit higher peak of total injections and withdrawals. They still meet our constraints. But again, the really neat thing is that the end user doesn't need to know anything about MATLAB. They're using all of the analytics that have been built in MATLAB to solve these problems in real time in Excel. Finally, one method we can use is to simulate the forward curve. So this is using a model for the forward curve that can be used to generate trials or simulate paths of the forward prices. So here we're looking at a few MATLAB visuals of those forward path evolutions. And what we can do basically in this method is to not just do a single optimization at the start like we did, but also update those positions as the curve evolves to lock in additional value. So this optimized rolling storage is going to step through and calculate those for all of those trials. As you can imagine, this is a very computationally intensive process because we're doing a number of optimizations for every trial times the number of trials. This is a little bit slow, so what I'm going to do is I'm going to stop this right here. And on the last tab here, I have some computation options. So instead of running this single-threaded, what I'm going to do is select a cluster. And what this is going to do is open up a set of workers. These are MATLAB workers on a cluster that I currently have access to. And I can still do this from Excel. When I come back to do my pricing, I can do it in a fraction of the time that it would have taken me running serially. So what we're looking at here in this plot is the value, the storage value for each of those trials. As you can see, as time progresses, we're able to lock in additional value, and these curves always move up and to the right. The black line shows the average value over time. So we get a sense of the average value, as well as some statistics like the risks or the variance associated with that number. So you can see we can very simply computed a few different methods for valuing that storage facility, be able to express our own insight, have um, advanced computation or scalable computation, and provide this to a user who's using Excel, who doesn't need to know anything about MATLAB, that can benefit from these analytics. So let's jump back and see how we can build these types of applications with MATLAB. So how would one go about building these types of analytics? We typically see that everybody who's doing this type of work follows this very simple three-step workflow that kind of nicely categorizes the steps that are required. The first step is accessing the data. As you saw, we pulled in historical forwards, options prices, and forward curves. But that data can reside in a number of different formats. It could be Excel spreadsheets, databases, data feeds, and we need to be able to easily and quickly connect to those and get the data that we need, do some cleanup, understand the missing data, for example, within those data sets, and start to analyze it. When it comes to analysis, there's a lot of different steps involved. Everything from building insight through visualization and exploration of the data, through quickly being able to put together models such as these to calculate the metrics that you need, and finally being able to build the applications around it. So in this case, all of the functionality that we had put together for Excel comprises our application. And finally, once you've done the analysis piece, the last step is to share those results, whether it's in the form of reports or, as we saw in this case, an application in an environment that's not MATLAB that allows you to the end user to do these types of use the analytics. And a big component to this is being able to automate this process so that in the future, if data changes, you don't have to do a lot of manual work to recompute your results and push them out to who needs to use them. So how this applies to our application? Well, we saw that we used natural gas forward prices, option prices, and historical forwards. We'll see how we can import those types of data sets in MATLAB and pre-process and analyze them. In the analysis, we started with model calibration, where we were looking at things like implied volatility, historical volatilities, correlations, understanding that the structure of the curves and how they behave, and then using techniques like optimization, Monte Carlo simulation, spread option pricing to actually perform the valuation. So we'll see how we can leverage all of those. And then finally, the outputs we produced were the actual storage value itself, and primarily what we've seen so far, the Excel application that took all of these functionalities and made them available to a user who's not using MATLAB. So let's now jump into MATLAB and see how we can build up these different pieces. So here's MATLAB. For those of you who are new to this product, I will demonstrate all the different capabilities and components of this environment as they become relevant. For now, we're going to start with the data because that was one of the first steps of that workflow. So this folder, this view here shows me the current folder and the files available on my system. I have a folder here called data that has some Excel spreadsheets. So for example, this one, NG Futures Price History, contains historical settle prices for different contracts of the curve. You can see it goes all the way from 2000. To import this data into MATLAB, all I need to do is pretty much drag and drop or right click and hit import. What that does is it opens up a wizard that we provide that allows you to interactively import that data. So it does things like convert spreadsheet dates, etc. I'll turn this to, I'll get rid of this for now. We'll leave it the way it is. So just with a couple of clicks, I can pull that data into MATLAB. So that's, as you can see, 145,000 observations or prices. The great thing about these tools, all of these interactive tools, is that they automatically generate code. So if you wanted to automate this process in the future, you can just click a button that will generate the necessary code that you can save and reuse to perform this operation in the future. To analyze data, you can issue commands. So for example, I can just type a command here, like calculate the mean of the settle price. Not that this really means anything, but this is the average forward price over 14 years of data, for example. But more interestingly, I've put together a few of those commands into what are called scripts, which basically just contain text files that contain annotations and some of those commands here. So what we're going to do is define some parameters and import that same file. So in this case, I'm using a MATLAB function to do the same thing. That's again going to read that spreadsheet and pull in all those 145,000 prices. But we only need prices between 2004 and 2014. So I'm going to use some of the indexing capabilities of this container called a table in MATLAB, which allows you to represent or store this heterogeneous data of text and numbers. It has a lot of great commands like filtering. For example, in this case, I'm just indexing into those where the date falls between this range. And I'm going to do another thing, which is kind of like a pivot operation in Excel, where I'm going to reshape my data, convert it from a tall representation into a wide representation. This will be clear in just a second. So if I run this, what I'm going to get is a new data set where instead of having a tall table with duplicate values of dates and symbols, now the symbols are across all of these rows. So I could actually just select some of these points here and do a quick plot to see the data that's been brought in. So you can see this is the evolution of that forward curve over time. And I can zoom in and actually see, what those elements of the curve look like. So you can see some contracts expire, new contracts get added. There's some missing data, for example. If you scroll all the way to the right, you'll see the effect of the crazy winter that we just had this year and the huge spike in some of the winter contracts. And actually, a more interesting way of looking at this is to generate a surface plot. And I've got a little function that does that. And it adds things like transparency and the ability to look at this in 3D. So we can actually see the structure of the curve and that seasonality that enables us to capture storage value, as well as the overall evolution. So we can also see, for example, the missing data structure, how in certain times you only had a few contracts. There's this big gap here that we're going to have to deal with. I really like MATLAB's graphics because they give you that ability to play with data and very quickly build some insight into what that data represents. So what I'm going to do is I'm going to just keep 24 months of data because typically so the gas storage contracts that we're looking at, they're just about 1 year. Finally, what I'm going to do is convert from this contract representation to promptness or maturity. So basically shifting the curve and looking at returns by promptness. So what we can see here is basically how the front month contracts are a lot more volatile than the further dated or the tail of the curve, as is expected. So we can quickly calculate some mean, covariance, standard deviations, etc. But just a side note here, while you're building all this functionality, you can get a lot of help in MATLAB to find all of these functions that you need. So for example, here in the command window, I can just search for missing data, and it'll list all of the functions that are available for working with missing data. So as you can see, a lot of the ones we're looking at here, computing mean, ignoring missing values, etc., are shown here. There's some more advanced functions like the ECM suite in the financial toolbox that allows you to do expectation maximization. But for our purpose here, we're fine with just the simple functions. So I'm going to calculate our correlations, volatilities. As you can see, there's a nice drop-off structure to the volatility. So this is again looking at it by maturity, or time to maturity. As you can see, there's a lot of structure in that correlation matrix as well. There's a very strong correlation, but typically the front month contract is a little bit less correlated than some of the later dated contracts. And finally, we can compare this to the option implied volatility. So I'm going to import another table here of options prices. And I'm going to use a MATLAB function, Black's implied volatility, the BLK-IMV function that computes the implied volatility using Black's model. So I can provide it the options prices, estimate the implied volatility, and then display that in overlaid with historical volatility. So you can see that while historical volatility kind of decays, the implied volatility represents a more accurate picture of the volatility of those contracts. For example, typically October contracts show a local peak because that's the start of the winter season. So we're going to use all of this data to compute our storage values, but as you can see in a few short lines of code, we've imported, processed, cleaned up, and generated the statistics that we need to go forward. Just on the note of automation, these scripts in MATLAB enable you to very quickly run through the whole process and generate results. So I could just hit run here and it'll run through the entire script, do all of the calculations. But I can take it a step further and use publish. This will generate a report that shows all of the results of the calculation in a nice formatted document. All of the comments within my code are translated into formatted text, and all of the figures and results that are printed to screen are embedded within there. So with just a click of a button, I can automate that whole process. So just in this script, we saw a little microcosm of how MATLAB enables you to go from that full workflow of interactively importing data, doing some analysis with the data, generating some output, in this case a formatted report, and automating that whole process. So if I wanted to stop here, I could just provide this report as an HTML or a PDF or something like that to somebody else. They can basically see the results of my analysis. Again, all of this was done in just a few minutes. So let me clean up here. Now that we have the data, the next step is to perform the analysis of valuing our storage facility. I'd like to take a couple of minutes to just provide an overview of the few methods that we'll be using. The intrinsic valuation method is kind of a standard or default method that's typically used. It just requires a forward curve, and we run an optimization to find an optimal set of positions in that forward curve that give us the injection withdrawals that meet the constraints of the facility, but that provide the maximum revenue. This locks in an initial value for the storage facility that doesn't change over time. It's fully hedged. The advantage is that it's simple to understand, it's easy to compute, but it chronically undervalues storage. The basket of spread options method treats the storage facility as a portfolio of spread options. A spread option being the option that pays out the difference between two calendar contracts. In this case, for example, a February and a July contract. So we use the implied volatility and the correlations between the different contracts to price a portfolio of spread options and then run an optimization to find the optimal positions to take in those spread options to maximize the storage revenue while still meeting the injection and withdrawal constraints. The advantage of this method is that it's fast and it captures the storage value, the extrinsic storage value. It also provides sensitivities that enable us to get a sense of the sensitivity of the storage facility to the forward curve and the volatilities. A third method, rolling intrinsic, performs a Monte Carlo simulation of the forward curve, and for each trial or each evolution of the forward curve, runs an iterative optimization that starts with the intrinsic value but then updates, rebalances the positions as the curve changes to lock in additional value. As a result, it always produces values that are greater than or equal to the intrinsic value and provides a nice spread or distribution of the potential future values that can be extracted from a storage as the forward curve changes. The advantage of this method is that, again, it captures the extrinsic value, but it can be computationally intensive. There are a couple other methods like spot optimization that we won't cover in this webinar, but if you choose to, you could absolutely program those up in MATLAB as well. So let's now jump into MATLAB and pick up where we left off and see how we can use these techniques to build some more insight into our problem and solve the storage valuation. So we're going to begin by just defining our storage parameters. So we have a facility with a maximum and minimum working gas volume. So we start out with a volume of 0. We have to return it empty. We can inject up to a total volume of 1 million MMBTU. We have specific costs for injection and withdrawal. So per MMBTU of gas, we incur a cost. In a second, I'll talk a little bit about those constraints for how much we can inject. Some of the other parameters here are things to do with trading, things like the liquidity spread between the contracts. So if I'm buying or selling, I don't get the same price. I have to pay at the bid or pay at the ask, receive the bid. And things like the initial curve and the number of trials for the simulation, etc. The initial curve that we had was similar to what you saw in the spreadsheet. It's a little bit unusual this time because of the depleted storage inventory. The prices are fairly high in the summer, so there's not as much intrinsic value based on the differences between the summer and winter contract months. You can see the following year's spring months have a much bigger spread. An important aspect that makes this challenging is dealing with these nonlinear constraints for injection and withdrawal limits. So what we saw in the spreadsheet was that you could withdraw or inject different amounts depending on the storage. These are daily injections, and because we're dealing with monthly storage contracts, we need to calculate what the total monthly allowance would be for injections and withdrawals for any amount of storage. As you can see, if the storage is empty, we can withdraw very little, but as it fills up, there's more and more that we can withdraw. Something similar for injection. What we're doing here is also finding an optimal approximation using a piecewise linear function that allows us to use linear optimization, which is much faster, and still deal with this non-linear shape of the injection withdrawal constraints. So to perform intrinsic valuation, I'm going to use this function that underneath the hood uses a number of our optimization solvers like linprog and intlinprog. Now you might be thinking, there's a lot of different commands I've been showing so far. How do I get help and how do I build up these applications when I'm doing this myself? The documentation is actually a very rich and very useful repository for learning how to use the product, finding information as you need it, and quickly getting what you need to move to the next step of the analysis. For example, in the optimization toolbox, it takes you from getting started, what is optimization, what does it mean, how do you to work with it, to figuring out how to use the right solvers for your problem. So these are all the solvers we have in the optimization toolbox. There's another toolbox called the global optimization that has more solvers for non-smooth functions. But in this case, we have a linear problem because we're just optimizing positions against a forward curve. And we have linear constraints. We use that splitting method of piecewise linear approximation so that we can use the linprog solver. In some cases, if we use minimum lot sizes, we also have discrete constraints or integer constraints, in which case we can use a new solver that was added to MATLAB optimization toolbox recently that allows you to do mixed integer linear programming. So these are the main solvers. As you can see, if you click into them, they give you a lot more information on how they can be used, with a lot of examples on how you can set up these problems, kind of taking you step by step from a kind of a mathematical specification to a more of a specification for the problem in the optimization toolbox. And that's exactly what we're doing. So our whole optimization function is about this long. It creates some of those constraints based on those curves and uses linprog or intlinprog depending on the situation. So in this case, I'm just going to run a basic intrinsic valuation. As you can see, there are injections and withdrawals, our total volume. We don't fill up the reservoir completely, which is the nature of the solution that it finds. But as you can see, we're well within our limits. We're not exceeding any of the injection or withdrawal limits, and the total intrinsic storage value is about 96,000. We can take this one step further and say, so for example, if you're dealing with futures contracts on NYMEX that have a minimum lot size of 10,000, we can specify that as one of the constraints. Now it becomes a discrete or a mixed integer problem. And if we run this, you can see that we get a solution that's very similar. It provides a value of about 95,000, but in this case, the storage and the injection and withdrawals are actually functions or are actually multiples of 10,000. So this is times 1,000, so it's 240,000 or 130,000 units that we're injecting or withdrawing. So these built-in solvers save us a lot of time because we don't have to do the actual math that's required to do the problem. It's kind of like building blocks. Those building blocks are available and we're just tying them together through some of these other commands to express our custom views, solve the problem, get the results that we need. The second method for basket storage, basket spread options, uses a number of different spread options and spread options pricers along with the optimization to figure out the optimal storage value. I have a slide here that just summarizes some of the different option pricing functionality that is provided in Financial Instruments Toolbox. There's a number of different new pricers that we've added in some of the recent releases, and this image kind of shows you for the different types of options, and more common options in energy, the models available. So for spread options, for example, we have Kirk's approximation, Berkton-Stenslen spread option approximation. There's an ADI method, that's finite difference. There's also a Monte Carlo method using Longstaff-Schwartz. So that's exactly what we're doing here. We're pricing a number of storage or spread options, taking optimal positions within those, and this is the result. So each box here represents a spread option. So for example, this one is a spread option that pays off the difference between January and September, minus a strike. And the strike here is the liquidity spread and the injection and withdrawal cost. And so the optimal set of positions is shown here in this diagram. As you can see, it meets our injection and withdrawal limits, but it's able to extract a lot more value. So why is there such a big difference? Well, the nice thing about options is that they can never have a negative value. So as a result, even if the volatility was zero, you would see that the implied intrinsic value based on the options that are in the money is still higher than the intrinsic value that we got from forward optimization. But the question that we had asked before was, how do you monetize this? How do you actually achieve this value? One of the ways of doing that is that you can actually sell this basket of spread options to a power marketer, assuming you get the fair value. but then you're obligated to make payouts depending on which options are exercised. But those payouts can be hedged because of the storage facility. So for example, if you are exercising an option that's the spread between July and January, you we take the opposite positions in the futures contracts on the date of that exercise. So you inject in July, extract in January, and you get positive cash flow because of that spread. And that cash flow should exactly offset the cash flow from the exercise of the spread option. So that's one way of monetizing it. And this visualization shows exactly those cash flows arising from the option position, the forward hedge, and storage. So this 280.27, that's the initial price of the value of the storage contract or the basket of spread options. Given which options are in the money, so to speak, the ones that have positive intrinsic value are likely the ones to be exercised. So assuming that happens, these are the cash flows that would arise from those options being exercised, and then these are the positions that we would take in the forward hedge. So in this case, injecting in July, August, September, October, extracting in December, January, February to offset the cash flows that we would have to make for the option exercise. So overall, the total value would be close to valuation using the basket optimization strategy. And I really like this because it gives you the way of monetizing that locks in the complete value. The other nice aspect of the spread options method is that it provides all of the sensitivities automatically from the spread option pricers. So here we can see the sensitivity of the storage value to changes in the forward curve. As you can see, it's negative for injection months and positive for withdrawal months, as you might expect, as well as sensitivities to things like the volatility. So if volatility of some of these contracts changes, we can get an idea of how that would affect the storage value. So if you wanted to hedge in different ways, you could you could basically do something like a dynamic hedging using these sensitivities. So those are the first two methods. Before we go into the rolling optimization, I'd like to take a couple of minutes just to look at the assumptions that we're making in that model. So what we had done before was calculate the historical and implied volatilities. As you can see, the historical volatilities in this case don't show any seasonal pattern. They just have a decay, as you might expect. However, if we look at correlations computed monthly, or volatilities computed monthly, we see some interesting features. For example, this is the volatility of each of those contracts grouped by front month. So when the furthest back row here is when the front month is January, the volatility of the January, February, March, and the rest of the curve. So you can see, for example, in January, the winter months have high volatility relative to April and beyond. And what's also interesting is the big drop off between October and November. And you can see that moving up in basically every curve up until this peak when October is the front month. So a lot of this structure and seasonality structure is lost when we aggregate and come up with a single volatility term structure. So if we want the most accurate model, which is one of our challenges, and be able to express our views, we need to be able to have a custom model that can represent this or capture this feature that we believe in. Another way of looking at this is visualizing the correlation matrix. So this is not just the volatilities, but also the correlation between the different parts of the curve. And you can see in the summer months, for example, that there's strong correlation between the summer months and between the winter months themselves, but not as much between the two. It's a very different picture in October, for example. But October front month is not very correlated with the rest of the curve. I say not very, but it's still pretty high. It's 0.7 or more for all of these. But if you look at the aggregated picture, all of this structure is lost. So what I'd like to do is have a model that can model all of these features. The last step is to reduce the number of factors. Um, as we saw before, there was a very strong, very high correlation. And so what we can do is use principal component analysis to reduce from a 12-factor 12 by 12 sigma matrix or volatility matrix to something that's a little bit less. So in this case, we can look at 3 factors. And that's a good number because, as you can see, 3 factors enable you to capture almost 99% of the variance in the motion of the forward curve returns. So just a few factors are necessary to capture the behavior of that curve. And so we're basically going to calibrate and save all of those models. So we're going to one that calibrates to a single historical, so the original single decay volatility structure, a single covariance matrix. A second model that uses forward volatilities or implied volatilities and historical correlations, but it's still a single model. And finally, our monthly model that uses monthly estimated covariance matrices that are each decomposed into 3 factors. So really the strength of MATLAB here is the expressibility, the ability to really express your views, create custom applications, and still build on a lot of the building blocks that are provided to do this in a fast manner. So finally, in our rolling valuation, I'm going to simulate that monthly model with 100 simulations. When doing simulations in MATLAB, especially for these types of stochastic differential equations, I recommend taking a look at a number of built-in functions that are part of the financial toolbox that provide a framework for stochastic differential equation simulation. So you can generate, for example, simulations with Hull-White-Vasicek, geometric Brownian motion, Heston stochastic volatility models by just specifying parameters. They could be time varying, things like the reversion rate, mean level, etc., and generating simulations from the resulting objects. And they handle all of the things like different time steps, antithetic sampling, etc. It really simplifies your life and enables you to do these things fairly quickly. So like I said, I'm going to generate 100 trials. As you can see, that was fairly quick. And I'd like to visualize these just to get a sense of what that simulation has produced. One of my favorite features in MATLAB is the ability to right-click, hit increment value, and just increment a parameter and see its effect locally within that section. So here I'm just varying the path and displaying the resulting simulation in this chart here. So very quickly I can get a sense of what that output of the simulation is. And you can do a lot more robust, statistically sound validations, like looking at the resulting distributions and verifying that they're log normal, etc. You can certainly do all of that in MATLAB. In my case, I'm just going to eyeball these curves for the purpose of this demo. So finally, the last step then is to run that rolling optimization, where for each case I look at one path and run multiple optimizations, rebalancing every week or so to lock in additional value. So if I run through this loop that goes through all of those iterations, we're doing something like 40 odd optimizations per trial. So there's something like 4,000, on the order of 4,000 optimizations that are happening. And we're still able to crunch through that in about 30 something seconds. So if you think about how many optimizations are happening, it's still quick. But as you can see, if you wanted to scale this up to 1,000, 10,000 trials, that this might not satisfy your computational needs. So what we can do is take advantage of parallel computing with MATLAB that enables you to take advantage of multiprocessors that are either on your local machine or on a compute cluster. And you can create, spawn these MATLAB workers that are maintained behind the scenes to do this computation in parallel. So the key thing here is that each of these iterations are independent. So when I operate on one trial, it's independent of what I do to operate on the other trial. They're not dependent between each other. So that took about 38 seconds. So what I'm going to do is open up a parallel pool. I could do it with my local computer, but I only have 2 workers. So I'm going to pick a cluster that we have access to and open up 16 workers. So you'll notice that these settings, these configurations for the hardware are unrelated to my code. So this code itself is portable. It can run on different hardware. So what I can do here is, instead of running a for loop, very simply convert this into a parallel for loop, which is a construct in the parallel computing toolbox that automatically takes the interior of this loop and runs it in parallel on that pool of workers that I have. The first time I run it, it'll do some analysis and figure out what data and files need to be sent over so that the workers have what they need. But after that, you'll see the computation occur much faster than when it was done locally. So we did it in 19 seconds. Let me run it again. Just because the first time I do it, it has to cache things. So you can see the second time around, it's a little bit faster. And in about 10 seconds, we're able to do that same computation. You'll notice that all of these things happen out of order, and that's really the key with parallel fors, that all these iterations are independent and they're computed in parallel in whatever order is selected by the method. But as you can see, very quickly we can scale up, take advantage of multiple hardware to do the calculations and the computation that's necessary. And as we saw before, all of this can be deployed to Excel. So even an Excel user can take advantage of the parallel capabilities of MATLAB. And finally, we can take a look at the overall rolling value. So this shows for each of those paths the value as it changed over time, how it was locked in by rebalancing. The black line is the mean at every point in time, and this distribution on the right shows the distribution of those values. So even though we might say, for example, that the storage value is 269,000, really there's quite a spread around that. So what could be achieved in practice may be above or below that original value. But notice that we can't do worse than if we don't do any rebalancing and stick with the original optimization, intrinsic optimization. So the solution here is basically an increase of 172,000 over the intrinsic value, but there is a distribution. So there is, for example, a 1% chance that the value may be under 110,000, which is still higher than the intrinsic value, but not near close enough to the average. So this gives you not just a point result, but also a sense of the distribution or spread around that. And that's it. So we saw all 3 methods of performing the valuation. The intrinsic had a pretty low value of 96,000. We were able to get much higher values with both the rolling and the spread option strategy, but they were very different in how they're able to monetize that storage and give you a sense of the risks from a hedging perspective or a planning perspective for the storage value. And again, all of this was done pretty quickly in MATLAB. We leveraged a lot of built-in capabilities. Let's now look at the last part in exporting these analytics to work in Excel. We realize that all of the analytics that you're building are not going to just sit on your desktop. So we try to make it very easy for you to provide those analytics to a number of people or distribute them in a number of different formats or integrate them with different enterprise capabilities that might be required. So you can take your MATLAB algorithms that you build, and once you've verified them, tested them, export them to work as desktop applications, spreadsheets, work with application servers, web applications, etc. There's a lot of different ways to integrate MATLAB into your enterprise. The key things about those capabilities are that it's a royalty-free deployment model. So whatever you create from MATLAB, whether it's an executable or a Java class or a .NET component, is free for you to do what you want with it. So you can distribute it as many people as you want. There's no additional costs or royalties associated with them. And again, the workflow is a very point and click, and it's the same workflow for desktop and server. So in terms of that simplification, we provide apps that enable you to simply select the target of deployment, add the functions to be deployed. So for example, in my case, I have functions like compute ratchet constraints, calibrate models, um, simulate forward curve, etc., that I'm going to deploy to be called from Excel. And with just a few button clicks, it will create the necessary libraries that I can export or integrate into Excel and provide to users. So I've already done this once, so I'm not going to let this run to completion. What I would get as a result is an installer that you can provide to others that'll install your DLL, it'll extract the runtime or download the MATLAB runtime as necessary. The files that are contained with that include an XLA, a BAS file, and a DLL. We also provide an add-in called the function wizard that allows you to very easily integrate these components into a spreadsheet. So you can take, for example, any of these functions that have been deployed, things like simulate the forward curve, for example, and tell it where all of the inputs for that function are going to come from in the spreadsheet. So for example, information on the facility, or where the output should go. And this will let you run those functions and automatically generate VBA macros that run behind the scenes. And that's exactly how I've set up this application. So all of the buttons behind this contain those auto-generated VBA macro that do the analysis. So anytime I'm doing my calculation, it's calling into a MATLAB component that's been deployed, that I've tested in MATLAB, that I've analyzed like we saw, and that's now running in Excel. And this allows me to take advantage of the full capabilities of the MATLAB solution, everything from MATLAB's optimization capabilities, pricing capabilities, parallel computing, visualization, and integrate them all in an application that I can give a front office trader or somebody else to do the calculations, get dynamic computation, and solve the business problems that your organization might face. So in conclusion, we saw how we could apply this modeling workflow to build insight, deliver analytics to our organization, but do it in a very limited amount of time. Be able to quickly get access to the data that we need, use built-in functions and a lot of the MATLAB capabilities like rich documentation, the interactive editor, variable editor, visualizations, etc., to quickly put together analytics, share results in reports, as well as build easy Excel applications that allow people to leverage all of those capabilities and expand our impact within the organization. So in conclusion, we had listed a number of challenges when it comes to building these types of applications, and hopefully you've seen how MATLAB is able to address some of these challenges. So for example, to extract insight and express our own views, we really saw how MATLAB was a fairly flexible, customizable application. You could really, we could look at those monthly volatilities and build and choose a model that really reflected our beliefs. There were a number of robust functions that we could use. All of them are very highly tested, production quality robust that we can leverage, rely on to do the calculation. It also saves us time because our job is to get some insight into the problem, use the right business know-how to put these things together, these building blocks together to create powerful solutions. We saw examples of how you could run fast Monte Carlo simulations and really scale our computation to solve challenging problems and even export those to Excel. the focus primarily was on modeling, not programming. We could do a lot with very little amount of code and build and deliver insights quickly. And finally, we saw how easy it was to take everything that we've created in MATLAB and export it to an environment like Excel that would allow a lot of people who are not MATLAB users to use the capabilities and, like I said before, magnify the impact of the analytics. Again, thank you very much for joining us on this webinar.